I'm happy to introduce Claudia Landi for the second talk in our Italian session of the conference, and she'll talk on discrete Morse theory meets multiparameter persistence.
Thank you, Herbert. Thank you to the organizer for having me talking here. Today, I'd like to talk about this topic that has interested me for the last years. This is more a research program, long-lasting research program than just one single piece of work. Indeed, I need to thank the many collaborators that helped me in this project at different epochs. The reason is that I believe that multiparameter persistence needs some geometric insights, at least for people like me, to understand it a little bit better. And I thought that maybe discrete Morse theory with its combinatorial properties can help in that task. During this talk, I'll give just the few preliminaries about multiparameter persistence and discrete Morse theory that I need for this talk, and then I'll give you the main three main results. I'll talk about the three main results that we have achieved in this research program. And then I'll draw my conclusions. So the first, when we started, we just wanted to try to accelerate persistence computations. What do I mean? So first of all, what is persistence? In the single parameter persistence, so when one starts with a data that gives rise to a simplicial complex or a cell complex, for example, which is filtered according to the measurements on the data, and then applying homology to this filtered cell complex, one obtains what is now called a persistence module, and it was called before persistent homology module. And then one studies invariants for these persistence modules, like the rank invariant, the barcode, the persistence diagrams. And what happens when the measurements are real valued functions, so we are in single parameter persistence, is that these invariants, the rank invariant, the barcode, and the persistence diagrams are all equivalent. So they can be obtained from each other. But what's more important is that they are equivalent to the persistence module. And so all of this came very natural in a single parameter persistence. Then people were interested in merging more than one measurement together. So one maybe has n measurements on the data. So the data maybe is still a simplicial complex or a cell complex, but can be filtered according to n different measurements simultaneously. And one can so get an n parameter filtration, so filtration of the simplicial complex, apply homology, and obtain an n parameter persistence module. And again, one can look for invariants. Now there are different ways of obtaining invariants. One is trying to decompose this module into indecomposables. And this is a very algebraic way of proceeding, and but it is also a very hard one because it is not so simple problem as it was in single parameter persistence. Otherwise, one can try to extract summaries of the persistence module, so something which is not equivalent to having the full information of the persistence module, but just a summary, which may anyway can be enough to study the data. And the kind of invariance one can study here is basically very similar to what one has in a one parameter persistence. So we again have the rank invariant. Instead of the barcode, we have the fibered barcode. I will define all these terms later. And instead of the persistence diagrams, one can have the persistence space. So in this talk, I'm interested in talking about these invariants, in talking about persistence modules, but as produced by this pipeline, not persistence modules by themselves. So that maybe the geometry we have here studied via discrete Morse theory can be useful to understand better what we have here. So when in this program, we work with simplicial complexes, K or cell complexes, and we consider n parameter filtrations of this simplicial complex, which means that we have a family of nested subcomplexes of K parameterized by a real by n real by a vector of Rn. And so it is nested in the sense that one subcomplex is included in the following one, where the ordering for the parameters is u less or equal than v, which means that the two multiparameters are less or equal than the corresponding ones for the other parameter for each coordinate I. We assume that we always start with the empty simplicial complex, and that when we consider all the parameters, we end with the full simplicial complex. So this is something that may be realized, for example, by filtering according to some functions defined on some monotonic function defined on the simplices of K. If we think of a monotonic function, monotonic with respect to the phase relation, then we have also this property, which is the key property in this talk, so that every simplex has exactly one entrax value in the filtration. So for each simplex, we can say when it has entered the filtration, and it can't enter two different for two different parameter values. Of course, when it enters, it always stays in the filtration after that. And now if we apply homology to each subcomplex, we always do this with the coefficients in a field. We obtain a vector space that is indexed by the parameter u, and because the subcomplexes are included into each other when u is smaller or equal than v, then we have also a linear map between these vector spaces, and the family of these vector spaces and the linear maps is what is called the persistent homology module, or simply the persistence module. To summarize this persistence module, one can use invariants. One invariant is the rank invariant, which just collects and encodes the rank of the linear maps that define the persistence module. So for each pairs of grades in the filtration, parameters in the filtration, U and V, with the U smaller or equal than V, this gives us the rank of the map between these two grades. And as I already mentioned, this rank invariant is equivalent to the persistence diagram and the barcode of the persistence module for one parameter persistence. But this is not true for n parameter persistence, because we can have two non-isomorphic persistence module which have the same rank invariant. And also there is no notion of persistence diagrams or a barcode. And so if we want to study the rank invariant using tools like persistence diagram and barcodes, we can slice the rank invariant along lines with positive slope. So in this space, we can, in Rn, we can consider lines through U and V, and we can restrict the persistence module to those lines, and this is what we call slicing the persistence, the rank invariant along lines with positive slope, where positive slope means simply that they are lines through two values of the parameters that are, so the lines are increasing according to this relation. And so if we restrict a persistence module, an n-parameter persistence module along a line, we obtain a one parameter persistence module, which is and the rank invariant of the n-parameter persistence module at values uv with the u smaller than or equal than v can be computed as the rank invariant of the restriction to the line at values uv. And the fibered barcode is simply a way of mapping each line with positive slope to the barcode or persistence diagram we obtain for this restricted one parameter persistence module. Now, the problem is that the set of lines to consider is infinite, so one doesn't know how many lines to compute to approximate nicely the full fibered barcode. And also, if we repeat the computation of a barcode for each line, maybe many computations will be repeated because basically we are reducing the boundary matrix, for example, by Gaussian elimination, repeating the same operations. So maybe we are wasting time repeating same operation for different lines. So, for example, these are two questions that we could try to answer studying things from the point of view of discrete Morse theory. And what is this point of view? Morse, what I use of discrete Morse theory is a very small part of it. The fact that we can classify simplices of a simplicial complex by pairing them such that if one simplex is paired once, it can't be paired again, and they can paired only sigma and tau can be paired only when sigma is a primary phase of tau. And in the pairing, we can't have cycles, so we can only have open paths if we represent this pairing by an arrow. And some simplices can also be remain unpaired, and in this case they are called critical. And these conditions is what makes a discrete gradient vector field, which can be represented by arrows. So an arrow from a simplex to a primary coface denotes one of these pairings, whereas, for example, this red circle around the simplex denotes the fact that that simplex is critical. So, so in this case, this is not a discrete gradient vector field because there is a cycle, whereas here there are no cycles. This is acyclic, the paths are acyclic, and so this is a discrete gradient vector field. The pairs in a discrete vector field can be used to define a simplicial collapse, and so reducing the simplicial complex we start from to something with less cells, even if it is not any longer a simplicial complex. Anyway, it has a smaller number of cells. And because this simplicial collapse preserve homotopy type, they preserve also homology. And so what one gets is that when we consider the cell complex containing only the critical cells, which is called the Morse complex, it has isomorphic homology groups that we had at the beginning. So this is all I'm going to use of discrete Morse theory. So I'm using much less perhaps than the theory. And now the idea was to use discrete Morse theory to accelerate the computations of persistence. To use Morse theory with persistence, we need to use particular discrete gradient vector fields V that are compatible with the filtration. And so this means that if a sigma tau is a vector in the field, then they must both belong to the same a subcomplex of the filtration. And so we had this result, which is basically the same result that Vidit and Konstantin had for one parameter persistence, only extended to n parameter persistence. So with Tomasz and Majid, we obtained this result that if we endow a multifiltered simplicial complex or cell complex by a compatible gradient vector field compatible with the filtration, then the Morse complex can also be multifiltered, and its persistence module is the same up to isomorphism than that of the original cell complex. So we can use only critical cells and their incidences to study persistence modules instead of using all the possible cells we had at the beginning. And so reducing the number of cells gives the idea that perhaps computations can be accelerated. And so later with Sarah, Federico, and Leila, we tried to have experimental evidence of this acceleration. And so we developed an algorithm to compute a compatible discrete vector field given a filtration, and applied it for computation of persistence modules with bifiltrations. And the algorithm used to compute persistence modules, both on the original simplex, simplicial complex and on the Morse complex, was the Topcat library developed by Oliver Gaffvert. So we used that library, and we computed for some spheres and some torus with not so many simplices as you see, and the Bell filtration, the persistence modules, and very often we couldn't end the computation, but if we applied it to the Morse complex, which has a reduction in the number of cells and grades to be of the filtration to be considered, then we could always end the computations. But of course, if of course, on the right, we are still using Topcat, and so if we increase and we reach these numbers of critical cells, again, we get stuck and we can't end the computations because this is a limitation in Topcat. But this at least gives a way of ending computations when at the beginning we couldn't. Also, we checked if reducing to the Morse complex can be useful for accelerating the fibered barcode computations. So when one slice, when one slices through lines. And so you can see that if we I'm sorry, because you don't see the bottom of this. Sorry, you don't see the bottom, I think, of this. So here, horizontally, there is the number of lines, from 4 to 100 lines, and vertically the seconds it takes to compute things. The blue graph is if we compute the fibered barcode on the original simplicial complex, and the orange one if we compute it on the Morse complex. And you can see that reducing the, and you also have the time where also the computation of the Morse complex is taken into account. And so you can see that really avoiding repeating computations on cells that can be collapsed allows to reduce the time. So we had this experimental evidence that considering only critical cells is beneficial also in multiparameter persistence, at least for computational reasons. And next, we went back to try to understand what is the information carried by critical cells of a Morse complex. And so we started studying the fibering of the rank invariant or fibered barcode using this Morse approach. And when the state-of-the-art paper, I think, about the fibered barcode computation is the one by Mike Lesnick and Matthew Wright, where they suggest that to compute the fibered barcode, one doesn't need to compute it for every line, but there are template lines that representative lines that can be used to compute template barcodes, and they are sufficient to recover the barcode along any other line. And to define the template representative lines or template barcodes along the lines, they use Betti tables of persistence modules, and they do so only for 2 parameters in the filtration. So with my colleagues, Asilata, Robin, Celia, and Barbara, we decided to use critical cells instead of Betti tables, and to work with any number of parameters. And what we got is the following. First of all, each time a critical cell or a critical simplex enters the filtration, we call it a critical value. It is a point in Rn, and we also take the closure of these critical values under the least upper bound. So for example, in this bifiltration, critical cells enter here, one more enters here, one more enters here maybe, and here also. And this is just, so these 3 are elements of C. The rest are only pairs that can be collapsed. And then there is this value in the parameter space, which is C3, which is the least upper bound of these values, C1, C2, and C4. And so this is our C bar. And this is the set that we are interested in. And for it, when we have a C bar, for each other parameter in the filtration, we can take the greatest lower bound of among the elements of C bar. And of course, the subcomplex under U can collapse onto the subcomplex under U bar, and so the rank invariants are the same. And so it is sufficient to study the rank invariant at this for these pairs UV with the UV belonging to C bar, and one knows the rank invariant for all other values of the parameter. But also one can try to study the fibered barcode using a C bar. And to do this, when you have a value of the parameter U, you can consider the positive cone, and you can consider its facet, the green facet of the boundary of the positive cone, the green facet, the blue facet, and the black facet. And you can check for each line which is the intersection between in which facet of the boundary of the positive cone the line intersects this boundary, and you can call this the push of U onto L. So for each U, you can define a point on a line with positive slope determined by the intersection between this the facet of the boundary of the positive cone and the line. And when you have this push, and you have these facets, the composition, you can say that all lines that intersect the same facet of U have the same reciprocal position with respect to U, to the point U, because they intersect the same facet, and you can define equivalence classes of lines. So 2 lines, when you have a C bar, the set of all critical values closed with respect to the least upper bound, you can say that 2 lines L and L prime are equivalent if they have the same reciprocal position with respect to all the points of C bar, which means they intersect the the boundary of the positive cone of each point of the C bar in the same facet. So L and L prime here intersect the positive cone of C1 in this facet, and the positive cone of C2 in this facet, and the positive cone of C4 in this facet. Whereas L second is not equivalent because the intersection of L second with the positive cone of C2 is in a different facet. And so we have an equivalence relation for lines with respect to their position with respect to C bar, and we can use this equivalence relation to see that for two lines in the same equivalence relation, there is a bijection of persistence diagrams. So if we consider the persistence diagram of the restriction of the persistence module to the line L and the restriction to the line L prime of the same persistence module, and L and L prime are equivalent according to this relation, then you can build a bijection between the two diagrams, because you can push critical points from line L to line L prime, and this is a bijection, and you can go back, and so you have a well-defined bijection or multi-bijection for persistence diagrams, equivalent persistence diagrams. This means that it is sufficient to know the persistence diagrams for one representative line in an equivalence class to later compute the persistence diagrams for all other lines. And so this shows that critical values are useful for reducing computations for the rank invariant, for reducing computations for the fibered barcode, and they can be used in the same way as Lesnik and Wright used the Betti tables. So now the question is, what is the relation between critical values and Betti tables? And this is the source of another work with Andrea Guidolin. And so first of all, Betti tables are tables that detect for each value of the parameter space, they detect the presence of birth, death, death of death, and they are algebraic information about the persistence module. And here the persistence module we consider, for example, are persistence module V of coming from a Q homology. And for n, these Betti tables can be computed using the Causal complex. I learned this from Martina Scolamiero, but then I saw that Lesnik and Wright used also this. However, following what Martina taught me and what I later studied because I was not aware of it, what is the Causal complex? It is for the case of with one parameter, one can consider the subcomplex at the value of parameter u, the previous subcomplex at the value u minus 1. Here I'm assuming that parameters are integer valued parameters times n, and we can consider the Q homology if I'm considering this the Qth persistence module, and I can build, and this is the map induced by inclusion, and I can this is a chain complex. I can take the homology of this chain complex, and so the dimension of the zeroth homology of this chain complex is xi0. Q is only for remembering me that I'm using HQ, and U tells me that I'm computing it at the value of the parameter u. And this is the dimension of the cocker of this map. So this is telling me that here something is born that is not coming from here. If I consider the homology here, and so I get the Xi1 Betti table, this is the dimension of the kernel of this map, and so this quantity tells me that something is dying when I move from here to here. So Xi0 captures birth, and Xi1 captures death of the persistence module, one parameter persistence module. In the case when n is equal to 2, one has to consider a square of values of parameters, and the Causal complex is a chain complex that defined in this way, whose homology gives us here Xi0, the number of births, Xi1, the homology here, the number of deaths, and also we have Xi2, the dimension of homology here, which gives us the number of deaths among deaths. And so we have one invariant more, and if we increase the number of parameters, we have n Betti tables. And what we could prove first with Sara Scaramuccia for the case n equal 2, and now more recently with Andrea Guidolin for any n, is that the number of critical cells that enter a filtration, where critical cells are measured by this relative homology, it bounds from above this algebraic sum of Betti tables. So the number of critical cells that enter a filtration gives a bound for the Betti tables. Here the Betti tables are all computed at, if we consider the number of critical cells that enter at the parameter u, at the value of the parameter u, all the Betti tables are computed for that value of the parameter. What changes is that in the Causal complex, we are considering Xi0, Xi1, Xi2, and Xi(n). And the persistence modules we are considering are the qth persistent homology module, the q-1 persistent homology modules, and so on. So we are considering many persistence modules at the same time, in the same grade, at the same value of the parameter. And so we have this upper bound, but because this dimension of relative homology captures, in a sense, the minimal number of critical cells, Q cells that enter the filtration at a time u, then we can also get a lower bound. So the number of minimal number of critical Q cells that enter the filtration at u bounds from below this other alternate sum of Betti tables. So this may be seen as an explanation of why with critical cells we may do the same that Lesnik and Wright do with the Betti tables, and also gives us some geometric, I think, insights on what the Betti tables can capture. So these inequalities are sharp, so we can find examples where they are equalities and all these values are different from zero, because of course when everything is zero, it is obvious that they are equalities. And to conclude, because I think my time is over, we are studying what critical cells of discrete Morse theory can tell us about more multiparameter persistence. In the future, we want to continue, and perhaps we want to study check if we can use critical values also to compute or define distances for persistence modules or for their invariants on one hand, and on the other hand, we want to make more precise the relation between the entrance of critical cells and the support of Betti tables. Because, for example, here we can have that this is a 0, this is 1, this is 0, and this is 1. And so we can see that without any critical cell entering the filtration, we can have two Betti tables that are not 0, and the rest are 0. And so it seems that critical cells do not capture when Xi2 becomes non-zero. But on the contrary, what we can anticipate with Andrea is that the problem in these inequalities is that we are considering only this degree of this dimension for the critical cells, and the fact is that the support of the Betti table is really included in the set of entrance values closed under the least upper bound. And this will be the topic of a upcoming work with Andrea. And so this is the list of papers that from which I've taken the talk of today, and I thank you very much for your attention.
Thank you very much for this beautiful talk. I see one cue in the chat by Marcy AD. Want to go ahead and ask a question?
Hello, and thank you very much for the interesting talk. I have a question about your gradient vector field. Can you extend your framework to the general combinatorial vector field when you are allowed to have non-trivial cycles? Because if you are concerning about computing homology, there is a way by Foreman himself, or recent way of computing floor homology of combinatorial vector field.
Sorry, I'm not sure I heard the full question. So I'm yeah, I think the last part of the question was about the floor homology. So I guess about
I'm talking. Sorry, I'm asking about extending. Is it possible to extend your framework to general combinatorial vector field when you are allowed to have cycles, non-trivial cycles? Why we are, I mean, isn't it related to something in multiparameter persistence, or why we are sure that there is no cycles there?
I am sincere. Honestly, I don't know this extension to the Morse theory when there are cycles, so I can't answer there. And so I'll look into that. Perhaps something I have not emphasized. So I'm sorry. It's an interesting question, and I can't answer now because I don't know the theory you are referring to. But I thank you also for the, so I'll look into that. I thank you also for this question, because I have not explained very well why it is important in all my talk, why this this condition here that every simplex has exactly one entrance value in the filtration is so important. It is so important because here, when I consider this, I want that If nothing has entered the filtration, then this union is exactly K. Is exactly KU, and so this is why it is important. But I'm sorry, I can't answer. I'll look into that and I'll get back in touch with you.
Thank you very much. Thank you. Thank you very much.
Oh, Jürgen had a question.
Yeah, my question is related to the question of Marzier, because not every function on a simplicial complex is a Morse function. And in particular, if you deform things, when you go from one Morse function to another one, you will go through situations where the Morse condition is not satisfied. And how could you handle, in principle, such situations? So when you change your functions, when you vary your functions, and try to go from one Morse function to another one, what would happen then?
Okay, maybe here my answer is that thank you, because this allows me to point out that what I'm using of discrete Morse theory is only a part of it. For example, we are not using Morse functions. We are using only these gradient vector fields. So only the pairing. There are no functions. The functions that are defined that give us the filtration, they are not usually Morse functions. But this is why we need to, so let me say more clearly, because maybe this is a bit confused. On one hand, I have the gradient vector field that only tells me that is independent from any function. So I don't need to define to have a Morse function to define this gradient vector field.
Yeah, but that is equivalent. If you have a function, if you have a gradient field, you can define an associated Morse function.
Yeah, on the other hand, when we want to filter, we have a measurement that allows us to filter, and we only ask for this compatible condition. And again, for example, if I have a monotonic function defined on K, this is not a Morse, may also not be a Morse function, but it is compatible with the gradient of a Morse function. So I don't know if this answers your question.
Yeah, so the question then would be, what would happen if you abandon that condition? Can you then still proceed?
The compatibility condition, you mean?
Yeah. In principle, you should still be able to apply some extension of your theory there.
Thank you for suggesting this. To us, in order to have this result, to have the maps that this compatibility condition seemed necessary, but I'll look into your suggestion and see if we can weaken this condition.
Yeah.
To us, it seemed this was necessary, because otherwise we couldn't make the diagrams commute.
Yeah, but I mean, there are extensions like Morse spot theory and so on, which you may possibly apply.
Thank you. I look in. Thank you. This is very interesting.
There's one more question by Stefania.
Yeah, thank you, Claudia, for the talk. I wanted to ask, in practice, how do you find the Morse function, or like the pairings of the cell?
Yeah,
do you have an algorithm that guarantees some kind of minimal? I mean, it's impossible minimality.
Okay, thank you. I decided in this 40 minutes I couldn't also talk about the algorithm, but yes, we have I might say we have too many algorithms, because when we started with Majid and Tomasz, we extended to n-parameter filtration the algorithm by Knudson, King, and Mramor Costa for 1 parameter persistence. But then we realized that it was a bad, at least it was bad for us, because we got too many critical cells. So in a later paper, which I didn't list here, with Tomasz and Majid, we extended the Vanessa Robbins algorithm for the algorithm by Vanessa for 1 parameter persistence. We extended it to multi-parameter persistence, and that looked very good. And then with Sara, Federico, and Leila, in this paper, they are they are computer scientists, and so could make a better job than I previously did, and so they optimized that algorithm. So I think if you want to find the algorithm, are interested in the algorithm, you could look at this paper that computes the discrete gradient compatible. And in this paper with Sara, for the case n equal to, so for any number of parameters, but for simplicial complexes of dimension up to 2, we prove that the algorithm, the 2020 algorithm we had, is optimal. So the critical cells are real. So there is the gradient is perfect. The number of critical cells is exactly that you need, the one you need to study the homotopy type of the 2-dimensional simplicial complex. And so this algorithm here, 2020, is proven to be optimal in this paper for 2-dimensional simplicial complex. And probably it could be also for some 3-dimensional simplicial complexes, provided some assumptions are added. For example, a manifold, for a manifold.
Yeah, thank you.